So now we're going to discuss attention mechanisms and the transformer networks. So these are the sources that I've used for preparing the contents of my slide. So first, to motivate what is the attention mechanism that we're going to discuss and why we need it, let's take the English definition, the verbal definition of attention. So attention is defined as a cognitive process of selectively concentrating on one or a few things while ignoring others. Okay. Whatever is in our purview of observation, we concentrate or pay more attention to some aspects or some things and ignore others. Let's take an example. For example, this is a class photograph taken from students for school. Suppose here, if we ask how many people are there, so what immediately goes on in our mind? We start counting the heads, right? Because we know if we count the heads, so we will be able to count the number of students as well as the number of teachers in this group photo. So what is our mind doing? Our mind is paying more attention to the heads. That is, while going through this image, it is automatically trying to extract features that help it recognize heads. So the something similar is also, we want something similar in our attention mechanism to be applied to neural networks or the machine learning architecture that we're going to discuss. So, and since neural networks mimic the functioning of human brain, the purpose of this attention mechanism is also to mimic this behavior of paying selective attention to certain aspects of the input data while ignoring the others, just as in this case where the goal is to count the number of people in the photo. So now suppose if the question being asked is, who is the teacher or who are the teachers in this photo? Now immediately what do? Our attention focuses from looking for heads in the photograph to photos of adults, photos of people with adult features, right? So immediately we start looking for people whose faces have adult features. So now we are paying attention to something else. Now we are not paying attention to just counting the heads, but we are actually trying to match from all the faces or all the overall the shape and size of the people in this photograph. We are trying to focus on which of all the people, which of those features in the photograph match with that of an adult. So we see again our focus change. So depending upon the task. So we want something similar to be incorporated in our RNNs or the attention mechanism in general for neural networks by dealing with such tasks. Example of attention where the relative importance of words is being captured. Suppose this sentence is being used for either a language translation task or for predicting the next word, okay, or for sentiment analysis. Okay. So it's important to capture the relationships amongst the words while processing this sentence. So we see here some words are more related to others some words are more related to specific words than they are to other words. For example, if we see the word eating is more related to apple, because what is the person eating? She's eating a green apple. She's eating an apple. The main thing is apple, right? Similarly, the word green also describes the apple. So it's strongly related to the word apple then eating and green are related to each other. Yes, she's eating a green apple, but essentially the word eating depends upon apple. Has she been reading a green book? Had she been reading a green book, we wouldn't have said she is eating a green book, right? She would have said she is reading a green book. So the word eating is more related to the word apple than it is to the word green. That is, if I'm processing this sentence for some other task, for where the goal is to sentiment analysis or next word prediction, when I'm processing the word sent eating, okay, when for the end task, when the word eating is being processed, due attention should be more attention should be paid to the word apple than to the word green. Similarly, when the word green is processed, more attention should be paid to the word apple. In other words, the one word is attending to the other words in the same sentence differently, right? This is the encoder-decoder architecture that we have discussed previously while discussing the RNNs and LSTM. So what happens in encoder-decoder? Just to recap, there is an encoder module which encodes the input sentence. Okay. In this case, the task is English to Hindi translation, where where the sentence "I am going home" is translated to "मैं घर जा रहा हूँ." And the output of encoder, which is the last hidden state, which is assumed to encode the entire sentence, is fed as input to the decoder. Okay, this context vector is supposed to encode this entire sentence. Suppose in decoder, and then decoder process steps by steps, producing the emitting the output at each time step, and it is expected to emit the desired output through this using these recurrent connections. Now it has two problems, both essentially stemming from the same fact that this context vector cannot remember long sequences. So one is because the context vector is taken from the last state of this encoder module, so it's obvious that the encoding of the earlier state is somewhat diminished or lost especially when the input sentence is long, right? Because the input encoding is only fed through this path, and if this path is long, then the input encoding would be lost by the time the encoder reaches this state. Okay. The second problem is, let's say even if encoding is all right, encoding is, let's say the input sentence is reasonably short, and this context vector represents this properly. By the time this context vector, so the same context vector is fed at the start of the processing of the output sequence, the production of the output sequence. So again, by the time it reaches the later parts, the context vector is diluted or diminished because it's passing through so many time steps. So let's say when emitting the word whom, at this time step, the model here, the neural network here, does not have access to the same context vector that the input sentence, the first word, while this architecture had access to while emitting the first word "मैं." Okay, so there are two things. The context vector does not capture cannot remember long sequences. The earlier parts are lost. And the second is that even the context vector is used for producing the output sequence. As the output sequence gets long, then even the second part, which was so what they did was they started feeding this context vector to every time step of the output, so that this vector is not diluted and every state has access to this original context vector in addition to the previous hidden state. But still, there was the same problem. The problem of that the context vector was not able to encode long sequences. because we're taking the last state. Apart from the fact that the context vector does not store the is not able to represent the longer sequences, that especially the earlier parts of the longer sequences. Let's say that even if we somehow make context vector represent the entire input sequence properly, still while producing the output, the in the decoder part, certain words are more attentive to certain words in the input sentence than the others. So it's not just about making the entire input sentence available to the to every time step to the decoder, but also about that the entire input sentence, all the words in the input sentence are not equally related to the output being the current output being produced. For example, if I am translating, I am going home to मैं घर जा रहा हूँ. So मैं, we know, is directly related to the word I. So it is more attentive to I. So if you are trying to come up with this some sort of attention mechanism which allows this at this time step when मैं is being produced, it allows it to give more importance to certain words in the input than the other. Then such a mechanism, such an attention mechanism should provide higher attention to the word I, which is represented by a solid line, than lower attentions to the other. We see the word ghar is more attentive to the word home than others. Right? We see word ja is more attentive to going than others, because ja means to go somewhere, and that is why it is more related to the word going. That is, it is so if the output, if the this decoder model was to produce ja, to emit the output correctly, it would focus, it will pay more attention to the input going. And similarly, when you talk about raha, then it represents an action, so it is related to going, and because of the first person, it is related to attentive to the word I, because मैं जा रहा था versus वो जा रहे थे. So because it is singular and first person, so it is more related to I, and because it also represents an action, it is more related to going than the other word. And similarly, when we talk about who, maybe who is more related to the word I and am, because मैं जा रहा हूँ rather than वो जा रहे हैं, and so on. So we see it's not just about that the context vector capturing the entire input sequence properly, but also at a particular time step in the decoder when producing the desired output, it may want to produce more attention to certain parts of the input than the rest. So there are two issues. Context vector is the last state. So earlier steps are not captured well, especially, and this problem is exaggerated, especially for longer sequences. The second problem is that relative attention to input words is not captured. So the solution to this is attention mechanism. So what we do in attention mechanism is we create shortcut between the context vector and the entire source input. Okay. So here is my, now if you see, here is the context vector. So this context vector is now not just being fed the entire the last hidden state of the encoder, okay, but it is fed, it is now has access to individual hidden states of the input. So now it sort of has a direct connection to the first word I am, second word am, third word going, fourth word home, and this direct connection, the amount of importance in individual words, or this direct connection is controlled, is parameterized through these weights W0, W1, W2, W3. So now this context vector is not just taking the last hidden state but also taking all the input states. So this context vector is now being fed at every time step. In addition, to decide how much what importance should be conveyed to this time step, at this time step, let's say which is the current time step where the word ja is being predicted, So now ja will want to pay more attention to the word going than to other words. Okay, so how to facilitate that for Ja is that one, that we connect all the words, all the input words with the context vector, but also we feed the previous hidden state from the decoder part. Now, so that now the context vector is a combination, encompasses two things. One is that it encompasses a previous hidden state as well as has access to all the words, all the input states of the encoder part. So now with the combination of this and this, the previous output state from the decoder pass and all the input state from the encoder part, which is fed to the current unit. So when it's being fed to the current unit, it is being fed through set of weights. There's a linear layer here. This linear layer can now decide, okay, if the current output which is being produced is ja, how much importance should I give to the words, input words, to individual input words. So the weights of these shortcut connections are customizable for each output elements. So what do we mean by this? Is that, so of course we have weights to these relative words, and we have also the previous output of the previous hidden state from the decoder part, and these are customized for each output element because by learning these parameters, which is being weights which are present here appropriately. So the context vector assumes encoder hidden states, that is all the hidden states that are somehow assumed or incorporated in this context vector. The decoder hidden states as well, right? The previous output states of the decoder, because Main and Ghar have been produced so far, and the next output that is to be produced is Ja. Main Ghar ja raha hun. So it should know that Main and Ghar have been produced. So not only it gets to know that through this direct connection, but also this previous output state of the decoder is fed to this context vector also. Now the context vector is in a better position to convey to the current output being generated, that is what is of importance, right? For example, if we remove if we remove this connection, then context vector will not get to know whether the current word is the next word, expected word is ja, output to be produced is ja, or it is ghar or it is rahu. So this connection from the decoder's hidden state gives this context vector an idea, okay, what has been produced so far and what is to be produced next. And this also allows it, to create a sort of alignment between source and target. What is alignment? What do we mean by alignment? We'll see. Alignment in simple terms means that Ja has to pay attention to which part of the sentence. So we are sort of aligning this word Ja with, let's say, word going. And this entire attention, this is how we represent this attention as a formula, which is it takes input the previous decoder state, and which is st minus 1, and it takes the context vector. Okay. And based on these two, it gives us attention scores. That is, what attention should be paid to the individual hidden states of the encoder. So this is the general formula for the attention. That is, the attention to be paid, at g, at the jth time step at the jth for the jth attention to be paid to the jth hidden state of the encoder at the tth time step. Okay. We'll see now. The next question is, how do we compute this attention score EJT? So there are different ways of computing it, which we'll see next. So before we see the ways of computing the attention, the same thing. So when we go to the next word, raha, so now the output from the previous the hidden state of the decoder is fed to the context vector along with context vector to compute the attention score. Okay. This proceeds for every time step. So this is what we mean the alignment. What we mean by the alignment between source and target. So this is an example that I've taken from the Bhanadu paper on attention, from translation from the French to the English sentence. So here we see the light colors, the lighter colors. So this shows word-to-word attention scores. In other words, word-to-word importance, relative importance from the word in the input sentence to the relative importance to the word in the output sentence. So we see the color, lighter the color is, the higher is the attention score. So we see the is more related to la, and agreement is more related to accord, on is more related to sir, and similarly we see. So we see these bright spots in the attention scores. Not only they give the relative attention scores, but they also sort of give the alignment between the source and the target. So before we mathematically formulate or discuss the existing techniques for attention mechanism, there's one more thing that I want to introduce, which is the concept of query, key, and value, which is a key concept of attention. So query, key, value concepts, they mimic the retrieval of a value bi from a query queue based on a key ki in the database. So in database, how does retrieval proceed generally happens is, we have set of keys which are sort of indexes, index word, just as in case of a book. On the back of the book we have set of index terms. So in database also, if you're trying to do a search on database for efficient searches, we have a set of index terms, and the corresponding value associated with each index term is listed in a mapping table from key to value. So the idea is that the key is compact representation. A key term and value actually represents the entire thing. Just as in case of a book, the index term represents a key term about a page, and the value next to the index term is given actually the page number, where one can go and know more about the key. So when we fire a query, the query is first matched against the keys present, and whichever key gives. When we match the query with the key, what we get is the similarity score between query and key. Then whichever, and based on this, then what we do is we find corresponding values, right? Whichever keys have a high similarity score with the query, they are selected to find the corresponding, to retrieve the corresponding values. So similarly, here we achieve the concept of attention through similarity between query and key, and then whatever the similarity score, we multiply the value. Okay. to get the overall attention scores between query, key and value. So first we get similarity between query and key, then we multiply it with value, get the similarity score. So this similarity between query and key can be calculated in many ways, based on which researchers have proposed techniques. Map this concept of query, key and value to the machine translation example, where we're translating from English to Hindi. So here, what are the attention mechanisms that we are proposing is that the context vector represents the has access to, assumes all the input encoder hidden states, and then it has the previous access to the previous hidden state of the decoder as well. So if we see in terms of query, key and value, what does the decoder want from the context vector or from the attention mechanism that we are trying to propose? So it gives as input the previous hidden state, which is st minus 1. Okay, previous hidden state, which is st minus 1. Okay, that is, it is giving the previous hidden state st minus 1 that as a query word, and based on that it wants it as output the relative attention scores to be paid to the individual input words. That is, relative attention to be paid to the hidden states of the encoder. Right? So what is the key here? The key is also the encoder hidden states. So this query is fired on the set of keys, which is the encoder hidden states, and we compute this similarity. And once we compute the similarity, we multiply the similarity with the value. What is the value here? The value is also the encoder hidden states. Right? So the key and value are here the same. So what we are doing is, given these hidden states, we are firing the key, which is the hidden states from the decoder side, st minus 1. We are saying, okay, this hidden state at the time step t minus 1 encompasses what has been produced so far, incorporates what has been produced so far by the decoder till time step t minus 1. So this is what I have produced so far till time step t minus 1. I am giving you this as my query, and you tell me for my next prediction, okay, at time step t, that is st, how much attention should I pay to your individual input words or the hidden states of the encoder. And this, so first we do multiplication between query and key, and then it is multiplied with the value, which is the encoder hidden states. So that gives us the relative attention score, which is parameterized through this linear layer and then fed to this model, this neural network layer, and it decides what is the output to be. So these are some of the well-known similarity measures. So this is additive, which was proposed by Bhardanu et al. In 2015, which is very popular. Then another popular one is dot product. So here we are simply talking about the similarity scores. Attention is obtained by similarity times the value. So this similarity between the two query and keys, where here W and B are weight matrices, parameters, neural network layers. And then the other one popular is general dot product by Long and scale dot product by Vaswani. So we will discuss a few of these. So the first attention mechanism is proposed by Danu et al. In 2015. So this is our encoder decoder architecture, okay, where the hidden state HT is computed as a tanh output of weight matrix times the previous hidden state and the UV weight matrix of the encoder times the input. So the tanh, this is typical what an RNN unit looks like. So here each of these units can be an LSTM or a GRU unit. In fact, in practice, this is what they are. And then at the output, at the decoder layer, we have the ST, which is the current hidden state, is computed as parameterized by weight times the previous hidden state and the previous output. So previous output is also fed as input. So it takes two things: previous output as input by t minus 1 and previous hidden state as input. Okay, and it gives the current hidden state, and this current hidden state is again parameterized through this VD and then through a softmax layer to present the output. So this is what the encoder decoder architecture that we are familiar with. Then how do we introduce attention? Is that while computing the current hidden state ST from previous hidden state ST minus 1, we involve context vector CT, which is computed based on all the hidden states of the encoder part through attention mechanism, and this relative attention scores alpha 1, 2, 2t and 3t. So one here is the attention score for the first hidden state and so on, and at time step t stands for the time step t. So this context vector, we feed it to this neural network model here. So now it has the previous hidden state as well as the context vector to decide what should be the next hidden state. Now, in the mechanism proposed by the Danu et al., this is how attention is achieved. So first, we compute the similarity score between the query and key. So what is the query here? The query here is the previous hidden state of the decoder part, ST minus 1 is the decoder part, and the key is the hidden state at the jth hidden state from the encoder part. So we are computing this similarity with all the keys. So what are different keys? Different keys are the different input words, which are represented by the hidden states here. So these hidden states, individual keys, we are computing the similarity between the keys and by query, which is my previous hidden state, through a neural network layer, which is weight matrix WA, passing through a tanh function, then another weight matrix VA. Okay. Then we are sort of normalizing this similarity score through this alpha. Okay, alpha like this, passing it through a softmax layer, and then this gives us the relative similarity score, and we are multiplying it with the corresponding value. Okay, so here this part is the similarity score, and this part is the value. So value is, again, you recall, as discussed in the previous slide, value is also the hidden state of the encoder part, hidden state from the encoder part. So what we are doing is we are computing the context vector, which computes the sum of attention to be paid to the individual, which sums the attention to be paid to individual words by doing a product of the similarity score and the value. Okay. So once we have computed this context vector CT, now it is the next hidden state ST is computing the next hidden state ST takes input as both the context vector time step t and the previous hidden state. So these two are fed through a neural network layer WD, represented by weight matrix WD. Plus, it also takes the output and produces the previous time step, which is YT minus 1. So this gives us the hidden state at time step t, and once we have the hidden state, we pass it through a softmax layer and through a weight matrix VD, the neural network layer VD. So trying to get into more visualizing these formulas through a more detailed diagram. This is what we have. The same formulas that we have discussed previously. So this entire thing is the attention mechanism. This entire thing is the attention mechanism, which is the shortened form of attention mechanism that we have represented in the previous slide. This has been detailed here. So what happens first is the previous output of the previous hidden state st minus 1 is used to decide the importance of the individual hidden states in the encoder parts. That is H1, H2 and H3. We assume there are only 3 hidden states. The input is of size 3. There are only 3 hidden states in the encoder part. So now this is the query, right? This is my query word. This is my query word. So first step we are doing is compute the similarity between query and the keys. So what are the keys? There are 3 keys, the 3 hidden states. So how we are computing the similarity? By concatenating them and passing them through a weight matrix, a neural network layer, which is represented by weight matrix alpha, W alpha. So this is the same weight, same parameters is shared, same weight matrix, same linear layer is shared across all the hidden states. So this learns, this training, the purpose of doing this is that this layer learns the similarity between the hidden state and the current hidden state H1 of the encoder part and the previous output at the decoder part, that is st minus 1. So this similarity is learned through this TANH. Okay, function neural network learn. So once these similarities is done, then they are passed through, which is this part, this TANH part. Once the similarity is learned, then it is passed through another weight matrix V alpha. Okay, so this here this vector we simply do a dot product. We do a dot product here. We do a dot product here to get these attention scores. Now these attention scores, before getting the final attention scores, so we get intermediate attention scores, EJTs, and before we get the final attention scores, we normalize these values through a softmax function, which gives an output between 0 and 1. So this gives us the final attention score, which is alpha 1, 2, alpha 2t and alpha 3t, alpha 1t, alpha 2t and alpha 3t. So once we have these attention scores, we multiply. Now, how do we compute the similarity? The context vector. Context vector is the product of the similarity score and the value vector. So this value is nothing but the hidden state, and this similarity is nothing but which has been computed so far using this alpha. So these alpha JT, this alpha JT represents the similarity score, and this represents the value. So we're multiplying the similarity score with the value to compute the context vector. So this is again, so this value is also being fed here, and we are multiplying with the alpha I1t, the similarity score, to compute the final context vector. And the final context vector is the multiplication product of sums of similarity scores and the values, which is summation of these. So this gives us a final context vector. And then to compute the hidden state, it takes input, the previous hidden state, the context vector, and the previous output of the previous time step is decoder, which are parameterized through linear layers as shown. So this previous output is parameterized through linear layer UD decoder part, where D stands for decoder, and this combination of this previous hidden state and this context vector is parameterized through WD, which is again linear layer at the decoder part. This passed through a TANH, so we get after this we get the current hidden state, current output, and this is again passed through VD, another linear layer, softmax layer, to produce the final output. So let us just, so we have discussed this much, and let us do a small numerical as to how to just to clear a concept further. So assume these are the hidden state vector values h1, h2 and h3, each is of dimension 2. Okay, and this is my previous output of the previous hidden state, okay, and this is the value of my current weight matrix WL, which is a 2 cross 4 matrix. and then this is my uh, attention. Just to compute the before we compute the final attention scores, we do a dot product of VA, which sort of does so this dot product. We have this, so one more linear layer which simply does dot product. So these things are given. These things are given. The rest have to be computed. So what do we do first? First we concatenate st minus 1 and h1, and st minus 2 and h2, and st minus 1 and h3, because this concatenation is actually fed to this linear layer WA, right, at the attention for the to achieve the attention mechanism. So this is the concatenation. So now we have my each of the input sample is of size 4. So that's why this weight matrix is of size 2 comma 4. So that when we multiply weight with this, we get an output which is of size 2 cross 1. So first we do tan h of weight times concatenation of st minus 1 and h1. So this is 2 cross weight WA attention matrix is this layer is this weight matrix of 2 cross 4, and this is 4 cross 1. So we get an output of 2 cross 1. Okay. And you can actually do these calculations on Excel sheet or on your calculator, whichever you're comfortable with. And then what do? We get the intermediate attention scores, which is simply nothing but the dot product of this one more set of parameters V alpha. So one more level of parameterization that we are doing. So when we get a dot product, so because dot product is a scalar quantity, so to convert it to a scalar quantity, so we do this dot product. So VA is also of size 2, 2 cross 1, and this product is also of size 2 cross 1. So when we do dot product, we get scalar values which are eventually passed through a softmax function which normalizes them between 0 and 1. So this is probabilistic output between 0 and 1. Okay. So now we have the relative attention scores in a probabilistic output where the sum of these values sum to 1. Okay. So now we have the alpha 1t, alpha 2t, alpha 3. So this denotes the relative attention to be paid to the individual words from the input size. That is, which are individual words at the input are represented by the individual hidden states h1, h2, h3 at the encoder part. So only this much part has been computed so far, the part that is represented in red. Next, what we do, we compute next. That is, we have computed only this much part of the figure. So now we're going to do further computations. So far what we have done is we have computed the similarity scores in the form of alpha JT values, and then we multiply the similarity score with the value which is the hidden state at the encoder part to get the context vector. This is the output of the attention mechanism. This is the output of the attention mechanism. Okay, so we're going to do calculations for the formulas in the red, or the one that is the block that is highlighted in the light red box. So this is what we have, h1, h2, h3 and st minus 1, and this is what we have computed from the previous slide, the relative similarity scores. So what is the context vector? Is the product of the corresponding attention scores with the hidden states, which are the values. So when we do this sum of product, we get, so this is my context vector. Now this context vector will be fed for computing the next hidden state as the decoder part, which is ST. So let's say the value of WD is as follows, the value of VD matrix is this, the value of UD matrix is this, and the previous output, the output time step t minus 1 is this. Okay. So first, what do we do here? So before feeding to WD, we concatenate ST minus 1 and CT. So now this becomes a four row. 1. So ST was 1, 2 cross 1, and CT was 2 cross 1. So now concatenate becomes 4 cross 1. And when we multiply with WD, so WD is 2 cross 4. And when we multiply with this 4 cross 1, we get an output of 2 cross 1. Right? So this gives an output of 2 cross 1. Similarly, UD is of size 2 cross 3, and the output vector is of size 3 cross 1. So when we do a product of these two matrices, we get a matrix of output as of size 2 cross 1. So these two outputs are added here. So we get an output which is of size 2 cross 1, and then they are passed to a tanh activation function. So the net output is of still size 2 cross 1. So this should be of the same dimension as the ST minus 1. So this till this point of time we have computed the ST. Once we have computed the ST, we simply compute the YT, which is that is the ST is passed through this the linear layer VD and a softmax function. So VD is of size 2 cross. So VD is of, sorry about that. So VD is of size 3 cross 2, and ST is of size 2 cross 1. So the product is of size 3 cross 1, which is the final output. So this gives us an end-to-end calculation of attention mechanism in an encoder-decoder. Mechanism that we're going to discuss is the dot product attention mechanism proposed by Long et al. So here, the everything else is the same as the previous attention mechanism proposed by Bhanadu et al. Only thing is to compute the similarity between the query and key, which is ST minus 1 and ST minus 1 and the hidden state J of the decoder. Instead of passing it through the neural network layers as shown previously, we simply do a dot product. Okay. Remember, the dot product between two vectors represents their similarity. Everything else is the same. So everything else is the same, but here this part is a lot simplified because we're simply doing a dot product represented by this operation, and then the rest of the part is the same. So again, let us solve a numerical. So these are the given hidden state values. This is the previous these are given hidden state values at the encoder part. This is the previous hidden state at the decoder part, ST minus 1. So when we we compute the similarity score, the intermediate similarity score as a dot product of ST minus 1 and H1, and similarly we do for hidden state 2 and hidden state 3. So once we have these similarity scores, we again pass to a softmax layer to normalize these values as a probabilistic output, and then we compute the context vector, which is the product of the similarity score and the hidden state. So this is my value, the hidden state from the encoder part, and this is the similarity score. So we do, and then once we have the context vector, again we do concatenation of the context vector and the hidden state output of the hidden state for previous time step at the decoder part, and assume these are the matrices VD, WD, UD, and YT, and YT minus 1, YT minus the output of the previous time step at the decoder part. So this is the same as was done in the previous example. So again we pass it through two neural networks layers, and then eventually to a tanh activation function to obtain the next output of the next hidden state ST, and then finally we use that to compute the output at time step T. Everything else is the same, just that the similarity mechanism is different here. Now the next that we are going to discuss is the another attention mechanism which was proposed by one of the PhD scholars at our department, CSC department in IIT Patna, Ashish Ranjan, who was working under my supervision. So recently he has joined as a faculty member at one of the quality institutions in India, in Odisha. So, so this is something we can be feel good about and be proud of. So here he proposed an alpha scale attention mechanism. So here, so everything else was taken from the attention mechanism proposed by Bhanadu et al. Only thing is, to after passing it through softmax layer alpha JT, it was normalized further. It was normalized to bring the value between 0 and 1. So what softmax does is it brings the value between as a probabilistic output. The sum of the attention score values is 0 and 1. But in certain cases, because Ashish was working on protein sequences, which can be very long and it can have lots of words. So these relative attention scores, because after being passed through softmax, their relative value, the absolute value becomes very less. Suppose in protein sequences can be very long, and the way words are defined. So if there are protein sequence of length 1000. So if we take words of size 3, so there'll be like 997 n mers, 3 mers. So 997 words would be there. So this for 997 words, this relative attention scores becomes very less for each word. Attention score for each word becomes very less because we have passed it through softmax, and softmax gives an output whose sum is 1. So it is bump up these values to rescale this value between 0 and to rescale these values between 0 and 1. So we divide it with the maximum value. When we divide the maximum value, these values are bumped up between 0 and 1. Okay, rest everything else is the same. So this helped Ashish particularly in case of protein sequences. Okay, rest everything else is the same. Let us do the same calculation. We have the hidden states from the encoder part, and we have the previous hidden state ST-1 decoder part. We weight matrix WA and VA. So we concatenate ST-1 and H1. That is the output from the previous hidden state at the decoder part, and we current hidden state, the ith hidden state of the encoder part, concatenate, then pass it through WA, weight matrix linear layer and tan H function, then multiply it through, do a dot product with another vector WBA to get a vector, to get a scalar output. And once we have scalar output, we pass it through softmax layer to get the, we pass it through softmax layer, this output. Then how do? We divide this value with the maximum value. Which is the maximum value here? Which is maximum value here is 0.37. So we normalize this value by dividing it with the maximum value. So when we divide maximum values, we see these values were small. Now they are bumped up to larger values. Still they are between 0 and 1, but bumped up to larger values. We have done that. Once we have these relative attention scores as per the new mechanism, we feed it to, now we compute use it to compute the context vector, for which we need WD. So sorry, WD would be required later, compute the final output. First, the context vector is computed as shown, okay, which is the product of attention scores as proposed by Yashi's paper, and the values, which is the hidden state. So we have this product, and once we have this product, we have these other matrices WD, VD, the output of the previous time step at the YT minus 1, and this matrix UD. So now what we do is we concatenate ST minus 1, the output of the previous hidden state, ST minus 1 and the context vector CT, and we pass it through this tan H layer, first through this linear layer parameterized by weight matrix WT, and then this linear layer parameterized by weight matrix UT. So this combined output is fed to tan H function, and which gives us ST, and then this ST output is passed to another linear layer VD through a softmax activation function to give final output as YT. So everything else is same, just that the way attention scores are computed. So after the formula is same as the Bhanadu et al.'s method, just that the attention scores are normalized to bump up the values between 0 and 1 by dividing with the maximum attention value. Another thing that Ashish applied was multi-attention. So in multi-attention, instead of having one attention layer, what we do is we have a set of multiple attention layers, parallel attention layer, and each attention computes significance of the words differently. Okay, and then we finally merge the attention, the score, using a summation operator to get the final attention score. So this is the this picture is from Ashish's paper that I have put here, just to show how different multi-attention scores correspond to the variation in capturing the particular words. So if we see one attention which is at the top, we see there are lots of words which are getting attention. So this entire thing is a protein sequence, and the individual lines show the individual words. So this can be considered as a very long sentence with lots of words. So we see that there are lots of words which are getting attention. So attention is sort of distributed amongst a wide range of words. When we do multi-2 attention, we see it is more focused. Okay. And same with 3 and 4 attention. We see in 4 attention, it is focused to even fixed set of, not fixed, but fewer set of words. So now we come to transformer networks. The transformer was proposed by Vaswani et al. In this landmark paper, Attention is All You Need, in the year 2017. So they have sort of replaced the RNNs in the encoder-decoder model. Okay. So instead of they have replaced almost a lot of, if not all, a lot of state-of-the-art models where previously RNNs like LSTMs and GRUs were used with the transformer model. Okay. And they also have an inbuilt encoder-decoder part, and they use all-to-all attention, which we'll see. So they don't accept the data in a sequential manner, but they accept it all at once, and they use all-to-all attention model. So let us straight away dive into the architecture of the transformer network. So this is the architecture of the transformer network. Don't feel overwhelmed by looking at this complex sort of architecture. We'll go through each of the sub-modules step by step. So it has two parts, the encoder part, which is the part on the left, and the decoder part, which is the part on the right. Okay. The encoder part for the multi-head attention part is actually shown here. Okay. So let us first discuss the encoder part. So the first input in the encoder part is the inputs are fed to the input embedding layer, so which is the word embedding layer. That is, the inputs here are fed as one-hot encoded vectors, which are converted to appropriate input embedding, and there are multiple ways to do that. How to convert to suited embedding. So once these input embeddings are generated, this is also a trainable network, learnable network, neural network, which learns the input embeddings. And what we do is next we add positional encoding to those input embeddings. So why do we need positional encoding? Because here the entire input is taken in one go, is accepted, is fed in one go to the encoder part. So encoder has no means to differentiate to how to figure out the order of the words, because all these set of words are fed as in one go. Whereas if you recall in RNNs, in LSTMs or GRUs, the input was fed one word at a time. So there was an inherent mechanism which allowed the RNN to understand that this is a first word that has been fed, and now the second word is being fed, now the third word is being fed, and so on. So it had an inherent mechanism to impose the order of the words. But here there is no such mechanism because the entire input is taken in one go. So we have positional encoding. We'll see how this positional encoding works. What is the positional encoding that has been proposed by the authors? So once we embed the positions of the word in the input embedding, then this entire thing is fed to a multi-head attention block, which is shown in detail on the left side. So this multi-head attention block, so here we see multi-head means there are multiple attention blocks. So this one attention block is this entire thing, and if you see the shadowed thing, so which denotes the multi-head attention, the multiple blocks. Okay. This is what we mean by multi-head attention. For simplicity, when we'll do the numerical, we'll just take one head. We'll assume there is only one head. So by the way, we'll also, apart from going through step by step, we'll also solve this entire thing in Excel step by step so that we get a clear picture of how data is flowing from one end to another. Okay, so coming back to this multi-head attention block. So this multi-head attention block uses the concept of query, key, and value, which we discussed earlier, to compute the attention scores. Okay, to compute the attention scores or the context vector. Right? You may recall the context vector is fed from the encoder part in the encoded code architecture. So here also the context vector is fed from the encoder part. So this multi-head attention actually is used to compute the context vector. So each of these Q, query, key, and value is computed, is trainable, is computed through corresponding weight matrices. That is a feed-forward linear layer. So there are three weight matrices to compute query, key, and value, and then we do the scale dot product attention mechanism, and then for multiple heads we concatenate their attention values for multiple heads, and then we feed it to a linear layer to get the final output. Again, the purpose of adding linear layer is to train it, to add more trainable parameters, to allow the system to train these concatenated values, to interpret these concatenated values in a trainable manner. Okay. Now, once the output of this multi-head attention layer is fed to add a normalization layer. So here two things are happening, adding and normalization. So first, to the output of the multi-head attention layer, we add the original input, that was input embedding plus position encoding, that is added to this, the output of multi-head attention layer. Now, why is it being added? So this is a residual connection. Okay, so if you are not aware of residual connection, so purpose of residual connection is as follows. Suppose this residual connection was not there. Sorry about that. So the purpose of this normalization layer is, suppose this multi-head attention was not there, then this input would have been directly fed to here, the feed-forward layer. And suppose this feed-forward layer says that I can do better even without multi-head attention. Okay. So if we don't provide, if we force the multi-head attention and don't provide this residual connection, then the upstream network will miss this opportunity to do better by directly dealing with the input. So to facilitate this, along with the output of the multi-head attention, we also add the output from the original input. So now you have both. Okay, you have both. So that's the purpose of adding residual connection. Now this upstream network, whatever is there, feed forward and the decoder part, has both options. Okay, it has a combined output. So that's why they have this residual connection which adds the output original input and the multi-head output from the multi-head connection. And then this is normalized and is fed to a feed forward layer. And from feed forward layer, the output, so feed forward layer, again we have one more add and normalization layer. So this feed-forward layer is a normal feed-forward layer. Its purpose is to predict better, to add one more customizable set of parameters. Okay. And then so this is the encoder part. Okay. The output from the encoder part is output of the final added normalization layer, which is fed to the decoder. Now we'll go to the. So next is the decoder part. So the first is what is the input to the decoder part? The input to the decoder part is nothing but the output embedding output produced so far. Okay. Whatever is the output is produced is fed as back as input. It is shifted right just to make things computationally right, because so that the next word is it indicates that the next word has to be computed. So suppose if the task is question answering, and the question is how are you, the answer is I am fine. So let's say I has been predicted or I am has been predicted, and the next word to be predicted is fine. So its input here would be I am, one shifted, one right, which indicates that the next word has to be predicted. Okay, so whatever is the output predicted so far, it is fed the same thing as fed as input. Okay, the same thing is fed as input to the decoder, as input to the decoder. So by the way, decoder works it's a regressive model. It's auto-regressive model. So it produces, works like RNN and produces output one time step at a time. So unlike encoder, where the entire input was fed as in one go, here the one output is produced one time step at a time, and the produced output so far, that is entire produced output so far, is fed as input. Okay, the output is so far. So first, like if I is produced, so I is fed as input. Then when am is produced, the output is shifted, right? And I and am are produced. Okay, then I and am are produced. Okay. So now then the next is the U has to be produced. So I am fed, and then U is produced, and U is also fed. So I am the next word to be produced is fine. So I am fine is produced, and then it is again shifted right. So now the decoder knows that okay, the end of sentence has reached. So it produces an end of sentence output, reaching which we know the production has to stop or the training has to stop. Okay. So the decoder, whatever output is produced, it's fed back as input to the decoder. Okay. Now the first thing after we get the output also passes through an embedding layer, and the first thing that happens is that it is we do a positional encoding, just as we did in case of encoder part. Positional encoding is done, and then this entire thing after positional encoding is passed through a masked multi-head attention layer. So this masked multi-head attention layer is same as the multi-head attention layer that was discussed in the encoder part, but there is an additional concept of masking. So the purpose of masking is that while predicting a particular token, the attention or access to future tokens should not be provided. Right? The access to future tokens should not be provided. That is, if I am producing, it shouldn't have access to future tokens. That is, let's say if I'm producing my answer, I am fine, which is in response to the question, how are you? So if the current verb to be predicted is am, I suppose I has been predicted, and the next verb to be predicted is am, then in that case, it should not be able to look up to fine. Okay, it should not be able to look up to fine. So fine has not been produced, but in terms of because this input is fed, entire input is fed, attention should not be calculated to attention should not be calculated of the current token with the future tokens which are yet to be produced. So that is what it means. The past attention should only be calculated with the past tokens that have already been produced. So this is the concept of masking. It is achieved by zeroing the attention scores of the current token with all the future tokens. Okay, so since we do all-to-all attention, so attention of all the current and the previously produced tokens is zeroed with all the yet to be produced tokens. This is what happens in masked multi-attention. We'll see how it is achieved mathematically. So once this masked multi-attention output of masked multi-attention is produced, it is again fed to an add and normalization layer. Okay, and here also we have residual connection, and then the output from here is produced to a usual multi-head attention layer, which is this layer is same as the layer that was here. But here we see for any attention layer we need query keys and value. The query is provided from the decoder part, whereas key and values are provided from the encoder part. Why is that? The intuition is, suppose I'm translating or I'm answering a question. The question is, how are you? And the answer is, I am fine. Okay, so let's say I have produced I am. Now I have to produce the next word. So I'm asking a question to my encoder which has the input. So encoder already has the context vector which represents the entire question. So I'm asking, I'm firing a query on the question, hey, this is what I have produced so far, that is I am. What is to be produced next? Okay, and the encoder has to answer that based on what was the original question. So it's sort of the encoder's job is, okay, the question was how are you, and he has produced I am fine. So knowing this question and knowing, how are you, so how are and you have already been answered, I am. Now how part is have to be answered, so it will give its input, which will be something like, hey, now the response to the how part has to be produced next. You have already produced response to the R and U part, right, which is I am. Now you have to give the response to the how part. So that's why the query is fired from the decoder part on the encoder part. And encoder has the set of keys and keys, and it gives the set of values. Okay, it gives the set of values to be produced. Now using this set of values, which are a sort of context vector, it knows, okay, now response to how has to be produced, and it already from this part it already has its own output that has produced so far. So I've already produced I am. Now I have to produce the next word, which is sort of a response to how part. Okay, so that is why this query key value, how the intuition behind how this query key value works in decoder part, why query is fed from the decoder part and key and value are fed from the encoder part. Okay, so now this is fed, again the output of this multi-head attention layer is fed to the add and normalization layer. Again this which is the original output from the previous layer, masked multi-attention layer, after being add and normalized is fed as through a residual connection, and then this is fed to a feed forward layer for more computations, and then again there's one more add and normalization layer, and the final output is fed to again one more linear layer, which is a feed forward layer, which having a softmax function for giving the desired output probabilities. So this summarizes how the decoder works. Okay, now we will go to these. Now next is the positional encoding. So the first question is, what is the need for positional encoding? So because in RNNs parse the word sentence word by word. So the words order is sort of integrated in the way processing is done, because first word is given, the next word is given, and next word is given, and when the next word is given, the hidden state or the cell state from the previous word is fed. So there is some mechanism which allows us to know this is the output that has been generated so far and this is the next output. So this ordering of words is inherent in the sequential processing of RNNs. However, the transformer takes all input at once, and for applying the multi-head attention mechanism. So entire input is fed at once. Okay, so that's why there is no order. So because entire input is fed at once, it doesn't know. It's not able to make out the difference between the order, that is whether I am a good boy or I am a boy good and so on. So we need to specify the order of the words in the input that we are given. Now one may argue that what is okay, we understand the encoder part, that there is a need for order in encoder part. What is the need for order in decoder part? Because the decoder generates the output one word at a time, which is true. But whatever the output is generated so far is fed as the entire sentence. Like if the expected output is I am fine, then sorry about that. So the same thing, because even though the decoder part generates the one word at a time, but the generated sentence so far, the partially generated sentence so far is fed in one go as input to predict the next word that has to be generated. Right? So the input vector length is fixed. For example, if I have to generate, the output has to be generated, I am doing fine. That says I am doing fine. So there are 4 words. So the input vector length is of 4, the decoder part. When the I is generated, the value of I is put in that slot corresponding to first word. And the remaining slots are initialized by whatever the random initialization was done earlier. And then the am part is fed. So now I am is fed, then the doing part is fed, and then the fine part is fed. So still, when we are feeding this I am in the sentence part as a sentence with all the words together in the vector, there is no ordering. We are not specifying the order. Okay, so there is no RMN like structure for while decoding. So that's why even the decoder part we need to specify the so what is the proposed? So the proposed method that has been given in the transformer paper, so proposes a d-dimensional vector, which is the same dimension as the input embedding, and this is not learned by the model. So this d-dimensional vector as actually positional encoding. Sorry. So this does not act as this is not learned by the model, but injected externally. That is, there is no way to enable parameters that learn these positional encoding, though later researchers have proposed learnable encodings as well. But in the paper, it is injected externally. So before we go to the scheme that they have proposed, it's a very nice, intelligent scheme they've proposed for positional encoding. Let us look at some of the alternatives which are not very viable. So let's say the first thing is that we assign a value 0, 1 to each value in the range 0, 1 to each position. Okay, that is, let's say if we have 20 positions, then we assign 0 position would be 0, first position would be 0.5, then second position would be 1.1, and then 0.15, and so on. Okay, so the problem with this approach is that the time step, whatever the delta, doesn't have consistent meaning across different sentences. And if one sentence is of length 10, then the time step would be 1.1, 0.2, 0.3, and if your sentence of length 20, it would be 0.05, 0.1, 0.15, and so on. Okay. Another approach is we assign integer n to the input at the nth position. That is, whatever is the word at the nth position, we assign value n at its position. The problem with this is the values can get quite large. Okay. Further, our model can face sentences longer than the ones in training. Suppose I fix till 1000 trainings, and in training the sentence's maximum sentence length has been obtained as 1000, and now we see a sentence in the testing phase is 2000. So my model doesn't know what to make of 2000, right? Because it has only seen values as 1000, doesn't have intelligence that 1000 times 2 is 2000. Right? It doesn't know how to make sense of 2000. And I think our model may not see any sample with one specific length, which would hurt generalization of our model. Okay, so our model may not see any sample with one specific length, which would hurt generalization of our model. That is suppose even if that is, let's say we have 10 different lengths in the range 1 to 100, but not every length may be sample of every length may be available in the training data, right? So So what is sort of a wish list for positional encoding that we are trying to come up to? So it should output a unique encoding for each time step, word's position in a sentence, and the distance between any two time steps should be consistent across lengths, across sentences of different length. Right? This is very important. That is, so if I'm taking difference between 4th point and 6th point, should be same as the difference between 10th point and the 12th point. Second is, our model should generalize to longer sentences without any efforts. That is, its value should be bounded. That is, we should have seen all possible values, or like it should easily generalize. That the encoding is such that it easily generalizes to longer sentences without any efforts. And last point is, it should be deterministic. So with these wish list, with this wish list in mind. So with that wish list, what they have used is, they have used sin x for positional encoding. So here a graph of sin x is shown. So on the x-axis we have the position, and the y-axis we have the corresponding embedding value. So we see for the position 0, the embedding value is 0. For position 10, the embedding value is also 0, and for position 5, the embedding value is 1. Okay. So the way the sin x graph is scaled, so y corresponds to 90, 5 corresponds to 90 degree, and the corresponding position value is shown as 1. The position for 5 is 1, and we see the position value for 4, which will be somewhere here, is 0.95. Okay. So this is a sin x curve. So there are two problems. So while this is a very nice scheme, looks like a nice scheme, can encode everything between 0 and 1. -1 and +1 not getting affected by extreme values, and this pattern so it conveys nearness between 2 points. There are two problems. So one is that when there's very little difference between positions 4 and 5, that for the nearby positions the difference is very less, just 0.95 and 1. So what the problem with this is that the model will not get proper idea that how far one is from the other, or is it really different? Is the position really 4 is different from 5? Another problem is that the position 0, 10 and 20 are the same, right? Because the corresponding embedding value is all 0. So this corresponds to sine of 0 degrees, this is 180 degrees, and this is 360 degrees. Okay. What they did was they add more sin x functions with a progressively lower frequencies or higher wavelength. So you see this sin x has a lower frequency, that is, it takes longer time to complete its one oscillation, right? So now my position vector has become two-dimensional. So if I have to compute the position embedding for 4th position, so we will do it like this. The 4th position would be a combination of these 2 points, these two vectors. The 4th will be represented by the corresponding sine value of the upper curve as well as the lower curve. So position 4 is now 0.95, is a combination of this and 0.74. Similarly, position 5 is 1 and 0.87. So now these 2 points are more different than they were previously if we just considered 0.95 and 1. Now they are more different. Okay. So this idea that they added more sin functions with progressively lower frequencies value. Okay, now another second problem is also solved. Now you see positions 0, 10 and 20 are not the same, because maybe with respect to the first dimension they are same, but if you see the second dimension, the second sin x function, they are not the same. See, 0 is this vector, 10 is represented by these two values, and 20 is represented by these two values. So while the first dimension may be same, the second dimension values are different. Now this also helps when the second sine function has same value. For example, if you see sine of the 0th position and sine of the 15th position and sine of the 30th position, they have the same value, but they differ with respect to the first sine curve, right? The position embedding differs. So this problem is solved. Both problems are solved. And to make it even better, they add even more sine functions, right? Like these as shown. So now each has become, there are four sine functions. So each has become now a four-dimensional vector. The positional embedding has become a four-dimensional vector corresponding to a particular position. To make it even better, they added even cos x. So why cos x? Because cos x is sort of in stark contrast to sin x. Right? Cos x is in stark contrast to sin x, in the sense if cos sine of 0 is 0, cos or cosine of 0 is 1. So it gives even better variations, even more variations are produced across positions, and they add multiple cosine values. So this is how the final function looks like. The function for in positional encoding in the transformer network. So if d is the embedding dimension, so it should be divisible by 2. That is, in how many positions, what dimensional position we want to add. So it is same as the input dimension. We will see why it is same as the input dimension. But whatever is the input dimension, d should be same as the input dimension. D should be same as the input dimension. So this positional embedding vector P subscript T superscript I. So T denotes the position. That is, what is the position of the word. For example, if the word is the third position, T would be 3, and I denote the ith dimension of the embedding vector. So here I will go from 1 to D. So for the tth time step, or for the tth position, what does the ith dimension of the position embedding vector looks like? It is sine of tau k times t if I is even, and is equal to cos times t if I is odd. So if I is odd, then I is equal to 2k, and if I is even, I is equal to 2k plus 1. So tau k is defined as 1 divided by 10,000 to the power 2k by d, where d is the dimension. So we see how is it increasing. So for the 0th position, I will be equal to 2 times 0, so k would be 0. So 10,000 to the power 0 is 1. So this tau k is nothing but just 1. Okay, this tau k is nothing but 1. So this goes as sine of 1. No, so whatever is the position, sine of that position. So this function becomes sine x. So because wk is, for I is equal to 0, wk is 0, 1. So this becomes sine of t, which is the sine of position, which is the first graph. Okay, and let's say when we are talking about the second position, so k is equal to 1. So when k is equal to 1, this becomes 2 by d. So it would be something little bit more than 1. The denominator would be something little bit more than 1. Okay, something more than 1. So this would be 1 by 10,000 to the power something. Okay, so this would give us the next sine wave with slightly larger wavelength or smaller frequency. That is, it will have a greater spread. Similarly, similarly as for cos as well, when the positional embedding, when the positional dimension takes the odd position, when I is equal to 2k plus 1, this becomes cos 2k. Okay, and for cosine function also, the wavelength increases progressively or the frequency decreases progressively. That is, the cos function also has a greater spread. So if you look at this function, this forms a geometric progression from 2 pi to 10,000 turn 2 pi on wavelengths. 2 pi, when is the wavelength, means how long is the sine wave. So default wavelength is, it takes 2 pi, that is 360 degrees, sine 2 pi, that is sine x, sine times the position, that takes 2 pi, and when it increases up to this much. So it forms a geometric progression. Then progressively it forms sine functions with lower frequencies or higher wavelength. And this is how the position vector looks like. So it's alternate of sine and cosine. So for even positions it is sine, and for odd positions it is cosine. So this is the final position vector which depends on D, which is the embedded. So this is a graph that I have taken from this blog, and it's a very good blog for positional in understanding positional encoding. I recommend you to go through it. So here, what he has done is he has plotted, the author has plotted the values of the positional vector. So on the x-axis we have the embedding dimension or the depth. So here it has taken 128 dimensional positional encoding, and on the y-axis we have the position. So it starts from 0 at the top, then first, 10th position, and up till 50th position. So we see initially at 0th position for alternate vectors there is not much difference because it's all sine. Okay, it's all sine, and these are the values, right? These are the values. It's all sine cosine. So on the top, the dark blue stands for +1 and the dark red stands for -1. So at 0th position, at 0th position, we alternate between cos and sine, right? So sine, the first thing is sine 0 is 0, so we have white color, and cos 0 is 1, so we have dark blue color. So we can see it alternates between 0 and 1 because the position that we are trying to encode is 0. So it's all between sine 0 and cos 0. So that's why we have 0 and 1. Similarly, as we increase, we see more variations in colors. So the point here is this entire thing, if you go horizontally, this entire thing represents the one embedding vector. So this entire thing represents the embedding vector for the ith position. The starting vector is for the 0th position, and this vector is the 128 dimensional embedding vector for the 50th position. Okay. So we see if I want to compare any two vectors, okay, any two vectors, we see there is some difference. There is some difference. Okay. Why the difference is caused by this? And at least the difference is in some dimension, some embedding dimension there is difference. For example, here there may not be difference because the sine frequencies are pretty much they are being zoomed out. They are not making any difference. So if you see with respect to embedding dimensions 80 and more than 80, they are all zeros and ones. Because of this, they are taking very small values. So this wave has gotten really, it is returning only 0 and 1 value. Whereas, as the embedding depth dimension increases, the sine and cosine waves becomes progressively very large with extremely large wavelength. So even at position, so at 50, they are not making any difference because there hardly any change. Okay? So we can see, but for any two position vector there is difference. So this gives the comparison. So the thing is that any two position should differ. So at least with respect to some dimension, any two positions differ. So this is the result of combination of sines and cosines. So the proposed method, the transformer add the positional encoding versus appending them. So this is another important point. So it's not like they are concatenated, but they are added. So why do they do so? So by adding means if this is the input embedding and this is the positional encoding, then they are simply added. The net output is the sum of this value and this value. So it's not concatenated that if this is 1, 2, 3, 4, 5 dimensional, this is also 5 dimensional, so this becomes the net becomes 10 dimensional. Though that makes more sense, right? Because somewhere when we add, so we would somewhere, because we're clubbing these two information, we'll be losing out on each piece of information, which is true, and adding this would have been better. But why they have done so is because the only reason that looks like what I could find is because it's computationally less expensive. Had they added these embeddings, the number of D dimension would have increased. So it's computationally less expensive. So that's why, because the positional encoding is actually added to the input embedding, it should be of the same dimension as the input embedding. The point that we had raised few slides back, why it should be of the same dimension as input embedding, because it is being added and not appended. So the next question is, how does it work? So what is actually happening by adding? Aren't we messing up both the input embedding as well as the positional encoding? Let's see. So the intuitive explanation is as follows. To understand the explanation what positional embeddings are trying to achieve, let's first understand what the word embeddings in general, how they work. So the idea behind word embedding, for example, word to work and glove and so on, is that to embed, let's say in case of English language, to embed the words in such a space, in such n-dimensional space, such that similar words appear nearby and dissimilar words appear far away. For example, king and queen are similar in meaning, so they should appear nearby. Whereas play and game are also similar in meaning, as represented by their colors as well. So they should also appear nearby. Whereas these are, king is different from play than it is similar to the queen. So these two words appear different than king and queen. Okay, so they are similar. So the purpose of embedding is it should be embedded. The word should be embedded in such a way that similar words appear together. They have similar meaning, and dissimilar words are far away. Okay. Now with that, suppose now we have to. So because we're going to add vector. We are adding, right? Dimension wise, we are adding the position encoding. So sort of we are adding. So this is all these words are also vectors. So we are adding one more vector to this. And what is that one more vector? We are adding the positional encoding vector to it. Okay. So what does positional embedding? What position embedding does is it moves a word at position I towards where words at position I tend to cluster. For example, consider two sentences: king, queen, and play game. Okay, there's just two sentences. The first word is king in the first sentence, and the first word is play in the second sentence. The second word is queen in the first sentence, and the second word is game in the second sentence. Now, these two sentences have to be, suppose we have to do positional encoding. So this word, when we will add a vector to the first word king here and first word play here, we will move it towards, by adding the vector, we'll tend to move it towards the position where all the words whose position is 1 generally tend to be. Okay, so it will sort of shift all the words in first position towards where the positional encoding says the words with vector on words on first position should be. Similarly, it will take all the words in second position and push them towards the position where the words at position 2 tend to cluster. For example, let's say this is the embedding for position 1. Embedding for position 1 is it's also a vector. It will be the same dimension as the input embedding, so it can be represented by this vector. So what this, and similarly, let this be embedding for position 2. So it will push these two words towards this vector where this vector is saying. Embedding position 1. Similarly, it will push these two words towards where the words with position 2 tend to cluster. So now king and queen are still somewhat similar to each other than they are to play and game. Play and game are still closer to each other than each is to king and queen. But now they have sort of incorporated their positional embedding as well. They have incorporated their positional embedding information as well. So this is the intuitive idea, that is, slightly move it towards where the words at that position tend to cluster. Now this movement shouldn't be a lot, so that the words, the original word embedding is lost, the relative positions are lost. At the same time, it shouldn't be too less, so that there is no indication of positional embedding. Okay, so this is the intuitive explanation. So now we'll go to the other modules of transformer. So just to recall, so it has a decoder part and it has an encoder part. So we'll go through this was the overall module. So far we have just discussed the positional embedding. So now we'll discuss the other modules. So the first part is the dot product, the attention mechanism. So in the attention mechanism, so the input is this is the input. The input embeddings, input plus positional embeddings is the input here. Okay, and then each is used to actually compute value, key, and query. Okay, so how they are computed? Through a linear layer of neural network. So here we have W, W, K, and WQ weight matrices is what it means by linear layer. So it allows us to train the input plus positional embeddings for the purpose of values, keys, and queries. So once we have that, then we do scaled dot product attention. How do we do? We first do matrix multiplication of Q and K, do similarity between Q and K, and then we scale it. We'll see what is the scaling formula. Then we apply softmax, so which gives values between probability value between 0 and 1, so the similarity value, and then we multiply with the values to get the context vector. Okay, this is similar to how we did in case of attention mechanism. Let's start going through the transformer network, the sample data, one step at a time. So values that are given in brown colored tables, brown colored tables are given. That is the values like input, how are you, and so on. And so these are the given values, and values that are given in light cream color, light creamish blue color, they have to be computed. Okay, so we'll see if we feed as input certain values, then how the data is processed through the transformer network. Okay, so let's assume that what the end-to-end task that we're trying to do is question answering. The question is, how are you, as it is shown here, and the answer would be I am fine, which we will see in the decoder part. Okay, so in this slide we will do this part, that is input is fed and it goes through the multi-head attention part, which is elaborated in the figure on the right. Okay, as we have already discussed this, so first inputs are fed, the input embedding is fed, then we do positional encoding, then KQV values are computed using the linear layer weight matrices, then we do multiply K and Q, we do scaling, and which you will see, and then we do finally do a softmax operation to compute the attention score. And once we have the attention score, we multiply with the V value to get the context vector. Okay, everybody get to get the context vector. Okay, so here, first step, these are my input values. So suppose each input is embedded in dimension 3. So corresponding to the word how, these are the 3 values. And suppose these are my positional embedding, position code. Okay, for 3 dimensions. Now these may not match exactly with the sine and cosine formula that have been given in the in the transformer paper, but these are just some dummy values for positional encoding. Okay, these are some dummy values for positional encoding. So now once we have this positional encoding, we simply add them to the input. So this is x is equal to input plus position code. So then it is nothing but a sum of the corresponding cell values. So when we take the sum, we get this values. Okay, now using this, the next step is to compute K, Q, and V matrices, right? So assume that the WK is the weight matrix corresponding to the key, WQ is the weight matrix corresponding to the query, and WV is the weight matrix corresponding to the values. So here one thing is important, that the dimension of the value matrix should be same as dimension of the input, right? Because eventually we are going to add a whatever is the output here, we are going to add input x to it as the residual connection that is here. This is going to be added. So that's why the dimension of the value matrix. So if x has 3 vectors, so it should also have 3 rows. If x has 3 rows, this should also have the 3 rows, and it will also have the same number of inputs, same number of columns as the number of words in the input. Okay, and the dimension of K and Q must be same. Okay, why? Because they eventually have to be multiplied to compute the attention score. Okay, so we multiply this input with WK to get the K, and we do matrix multiplication of WQ with the input X to get the query value, and then we do the matrix multiplication of WV to get the value. We matrix to WV with the input to get the value. So this is the result is as follows. So WK is of size 2 cross 3, input is of size 3 cross 3. So when we multiply this, we get K, which is of size 2 cross 3. So where each word is embedded into a dimension of size 2. So in value, each word is embedded into dimension of size 3. This must be same as the input dimension, only then it can be added in the residual connection. So once we have this, okay, then we simply take the transpose of V. We just do this for convenience because eventually we will have to multiply V here. So that's why we take transpose, so that the alignment and correct values are multiplied. So what is the next step? The next step is, so this is my Q. I take the transpose of Q transpose here, so that it can be multiplied with K properly. Okay, to compute the similarity score. Okay, so we compute the similarity score using Q cross K here, and we add a scaling factor which is under root dimensionality of K. So dimensionality of K is 2. So this is just a scaling factor, okay, to scale the values, which is this operation. So first we do matrix multiplication, which we have already done with K and Q. We are doing it all the thing together in this slide, but first we do Q multiplication of query and K, this matrix multiplication, then we do scaling by dividing it under root of dimensionality of 2, and then we pass it through a softmax. So all these operations you can do with Excel, and you can check the values should be correct. In fact, 99% they should be correct. I have checked it, and I have also I've done in Excel, but maybe if there is any mistake, just feel free to drop me an email. I'm a human, I can make mistakes. Okay, so this gives us the softmax value of Q cross T, which is this output. Okay, and then once we have, so this is the attention score. So once we have the softmax value to obtain the final, context vector, attention context vector after the similarity, after the attention mechanism, the context vector is attention times value. So this is the attention relative importance of queries and keys through attention mechanisms, and we multiply with the value matrix. So we multiply the value matrix like this. Okay. So yes. So this is this is attention score query times key. So here words are represented as in the row form. So when we do this, when we multiply this with the value, so here we are computing word to word, word to words with this query times t similarity score. We are multiplying with the value to get this matrix. Okay. So here you see we are multiplying this with V transpose. That is, this entire thing is being multiplied with V transpose. Okay, So you see, this gets multiplied with this gets multiplied with this gets multiplied with this. Okay, so this value represents what is it retrieved in response to how. It all the three retrieved value for the first position. Similarly, R, this is multiplied with this is multiplied with this, and this is multiplied with this. So this represents, R represents retrieved value with respect to, at the second position with respect to all the three words. Okay, so that's how we do it. Okay, had we simply multiplied this without the transpose, so this wouldn't have made sense, because this means this gets multiplied with this gets multiplied with this, and this gets multiplied with this. So we only get to compute similarity of how versus how only, which we don't want. We want similarity of of result of query of how with respect to all the three terms. So that's why we do transpose here. This is just for you to, I just emphasize on this so that you may remember that we have done B transpose, so that the words are actually represented as rows, and here also the words are represented as rows, and then we do multiplication. So with this we have got the context vector, so each row is a vector representing words. So now we have got this FKA view, so that is we have computed this multi-head attention part. So next is multi-head attention. So this is one attention mechanism. Okay, this is one attention mechanism, and when we have multi-head attentions, it means simply that we have multiple heads and their output is finally concatenated. For example, here we have considered two-head attention mechanism. So for two-head attention mechanism, we have the key query and value part is also split into two parts. Okay, so let's say the key part is split into two rows, two dimensions. So first row becomes 1K1 and the second row becomes K2. Similarly, Q1 becomes first row, Q2 becomes first row, and for value we are saying this, because the first two become value 1 and the second becomes value 2. So just because it is 3, so we have to divide it in 1, we'll get only 1 and the distribution will not be equal. So in general, if we have n heads, we can divide these K, Q and P matrices if we want n heads like this. And then we do the same operation for the multi-head attention part. So just as we did in case of the normal attention. So the operations are the same, just that after splitting the matrix, whatever we get, context vector that we get FKQV, V and Q2V, we simply concatenate this. So this comes from the green part, this, and this comes from the khaki colored part. Okay, here it comes here, and then we simply concatenate it. So the advantages of this multi-head, it is inherently parallelizable. It can be easily parallelized, which gives a lot of performance speed up to transformer network. This part, this multi-head, because it can be parallelized very easily. Right? So, and in general, matrix operations are very parallelizable. So this entire thing, because entire input is taken at once, and there's no sequential dependency. So transformer architecture in general leads to easy parallelization. Okay. This means multi-head, same as the attention mechanism that we did in the previous slide, just that now we split into subparts and we concatenate the output. Okay. With that done, we move on to the further part, which is add and normalization feed-forward network. So this is we had the this is what we had, the context vector after applying the attention mechanism, context matrix from the previous slide, and this is my X plus input plus positional coding. So these are computed. So this is my X transpose, and this is my context vector plus X transpose. Right. So first we are doing normalize, adding residual connection. So whatever the input is gets added to the output of the multi-head attention.
So because X plus input code was like this, we do transpose first because this has words along the rows. So that's why we do transpose. So we add this to this, so we get the add, and then we do normalization, which is Z normalization, feature wise Z normalization, which is X minus X minus. So here we do normalization, which we do Z normalization, which is X minus subtraction from the mean and divided by the standard deviation. Okay, so this gives a zero mean and puts the variance to unit one variance. Okay, that is this part. So the output of this part is this. Okay, and then this is added through a feed forward layer through a ReLU function, and it involves weight matrices. So there are two weight matrices. One is WE1 before being fed to the ReLU, before being this output after being added and normalized. This output is again passed through a feed forward layer which having weight matrix WE1, and then the ReLU function is there, and then the output is again fed to another matrix, is passed through another matrix WE2. Because suppose these are the values of the two matrix. So after this output, we have a feed forward layer which consists of two matrices. So we get a ReLU layer, we pass through it through WE1, so and then to a ReLU function. ReLU function is nothing but defined as follows, and then there is WE2. So this output, feed forward layer output, network output at the encoder part is the output that is here times this matrix WE1 passed through a ReLU function, and the output of the ReLU function is passed through another linear layer which is WE2, and this gives the output of the feed forward at the encoder part. So this is the output. Once we get this output, we do transpose because we have to add X to it. Okay, so this is how X is here. So we do transpose, we add X to it. After adding X to it, this is the output that has been added. So not the original input X has not been added, but the X that was produced at output after the add and normalization of the multi-retention part. So this X is being added again here. So this here Xi is actually Xi. So this is the output of the add and normalization layer, that is this output. Okay, this output is sorry, not this output. Okay, yeah. So add and normalization layer. Yeah, this output. Sorry, yeah, this output Xi, which is the output of the add and normalization layer, which is this output after this layer. This is output. So this gets again fed back here as a serial connection. So this output is being added again here, and we do add and normalization. Okay, we do normalization just as this, and after normalization we have already done add, and then we do normalization. So this becomes the output of the encoder part. Okay.
So before we get started with the decoder part, we need to understand that in transformers, the decoders work like RNN. That is, they produce one word output at a time. Though they take the entire input at once, unlike RNN, which process one unit of input at a time, in transformers, the decoder, even though they take the entire input, all the words of the input at once, but they produce one word of the output at a time. And the animation on the left side tries to give an idea how decoders produce output. So we see initial, so they just as in RNN, they take as input the output that has been produced so far. So in the RNN, if you recall, in the decoder part, the last produced output, that is output word that was produced at the last time step, is taken as input. But here the transformers take the entire output that has been produced so far. For example, here they start with start, then I,
then am, then find. Okay, and they take this and they produce one word of output at a time. Because they produce I, then am, then find, and then this is the end marker, which shows that all the outputs have been produced and the decoder stops decoding. However, they take this entire input at a time, but they pay attention to the different parts of the input differently. Okay? For example, when they are producing word I, okay, which will just come. So after they produce start, they produced I. So see, I pays more attention to U, okay, which you can see from the animation that when the I is produced, is about to be produced, this word U is highlighted more. Okay. Similarly, when they go further, when they produce am is related to R, and so on. How is related to find, and so on. So they take the entire input at once, and that is fed to the decoder part. That is here through this connection, that is fed to the decoder part, and then the decoder produces one word output at a time while deciding how much attention is to be paid to the different parts of the input words, right? Like hi, how are you? So it starts with the start token. The first input to the decoder is the start token, which is just a token which says that the decoder has to start producing the output. So that's why the start and end have a special token. Start, and what we get here, it will just come, is the end. Okay, this is the end token. They have special meaning. So when the transformer starts with gets the input at start, it produces I. Then in the next time step, it gets input I. That is, this input goes here. It gets input as I, and it produces am. Okay, it produces am. Then in the next time step, this am goes as input here, and it produces find. And the last time find goes as input here, and it produces the end of the sentence block. Okay, so this is how the decoder works. I just want to bring this up. So while they take the entire sentence as input at once, but they produce output one word at a time.
Now we come to the decoder part. In the decoder part, we have we first will discuss this part where the output input is fed, and then it goes to the multi-retention, mask multi-retention part. So here the input is the output that has been produced so far. The input is the output that has been produced so far. Okay, shifted right. Shifted right means it is produced one time step at a time. So in that sense, decoder works in a sequential manner. It produces output one word at a time, and whatever output has been produced so far is fed it back again. So it is shifted one word at a time to the right side. So example, initially when nothing has been produced, all the vector would be of size 3, because the transformer has to know what is the size of the output, maximum size of the output. So output vector is initialized as 3, and then once that is done, so 3 is decided. So these 3 values would be initially random numbers, randomly initialized. So once they are initialized, then it is fed to this input, and then it will produce, let's say, the first word I. So when I is produced for the next time step, this I is filled here. The value corresponding to embedding corresponding to I is filled here, and these two will be, the pointer will shift to right, that is, which will indicate that now this next word has to be produced, and the slots corresponding to am and find would be initial random numbers, which are initial values. So similarly, when find is produced, value of I and am would be filled in from the output that has been produced so far, and the pointer will shift towards the right to indicate that find has to be produced. Okay. So now this input vector is fed, it goes to the output embedding, then there's positional encoding, and this goes to the mask multi-retention. So let us do the calculations. So this is, suppose, my output, the encoders for the size 3. So I've just put I am find for convenience. However, initially I and then am, then I am, then find would be generated. So these are my inputs. So this is the positional encoding. We add the positional encoding, we get the output. Here we compute Y transport for convenience, which will be needed later.
here in this point. So now we have the output plus positional encoding. Now we need to compute k, q, v values. So we have the corresponding weight matrices shown here. Dimension of k and query should be same, which is 2 here, and the value dimension is 3, which should be same as the input, which is of dimension 3. But then we compute k, q, and v matrices using the matrix operation, matrix multiplication, and then we apply attention. So before applying attention, we compute the similarity score between q and k, and we normalize the similarity score by the under root of dimension of k. Dimension of k of the key is 2. Each word is represented as 2, so we normalize it like this, and then we add mask. So an important concept is here is mask. I will tell you what mask means. So this is my attention score. This is my query. We do query transpose. We have to multiply it with key. We already have key matrix here, and then this is a mask matrix. Okay. So what does masking do is, masking says by paying attention to tokens should not be allowed to pay attention to future tokens. Okay, should not be allowed to look ahead. They should only be made to focus on what has been produced so far. That is, when I am producing am, the network should only be allowed to pay attention to the words that have been produced so far, that is I. Similarly, when we are predicting find, the network should only be allowed to pay attention to I and am. So to do this, for future token attention scores, we add a negative infinity value here in the masking. So what happens in negative infinity is, when these negative infinity values are added to this product of q and k, okay, and then when they pass through this softmax, the corresponding values are zeroed. Okay, the corresponding values are zeroed. As you can see, these three values are 0. Here, these three are negative infinity. Now, what are we doing is, what it says is, when I is to be produced, it is allowed to pay attention to itself. It's all right. Okay, but it is not allowed to be pay attention to the future words, that is am and find. So that's why these two values are negative infinity. Similarly, when am is to be produced, it can pay attention to the previous word and itself, its current position, but is not allowed to pay attention to the future position. That's why this find is negative infinity. But find is allowed to pay attention to all the three words. So this is what it means, that it is not allowed to pay attention to future values, future tokens. So when am is to be generated, find is a future token. So am is not allowed to pay attention to find. So that is what is achieved through this masking. So once we have this masking, we do query plus k, we do query times k, and we do masking and do softmax. So this gives my attention score. Okay, and once we find an attention score, we obtain the context matrix, which is attention times value matrix. So we get this FKV, and once we have this output of mask multi attention, so we do add a normalization. So first we add the YT value. So this is through here, through this position, we add the YT value, that is this value transpose. So value is first transpose, because here each word is represented along row. So this value is transport value is added. Okay, to get this, and then we do normalize feature wise using the Z normalization that we discussed previously. So now we have this. So with this, we get the output of add and normalization from after the mask multi-head attention. The next part is, we have one more multi-head attention layer. This time there is no masking. So masking is only in the first layer. Now there is no masking. So here the key point is, query is done or provided by the decoder on the key and values provided by the encoder. Okay, so it is like, hey, I have produced I so far. I suppose the sentence is I am fine. I have produced I and am so far, which becomes my query. You tell me what is to be produced next. So the sentence has learned the context of the encoder has learned the context of the question. That is, how are you? So it says, okay, how are you is the question, and the answer in the answer I am has been produced. So next word should be fine. So on the basis of that, it provides the key and value. Okay, key and value provided. So key is, and so the search and retrieval is done on the encoder part by the decoder. So it fires a question. The query is fired by the decoder part. It fires the query, this is what I have decoded, what next should I produce? And it gives an answer. And that answer is used to the feed forward net to generate the actual output. Okay. So this takes, so suppose this is my output from the encoder side XC, how are you? And this is my intermediate output from the, after the first multi-mass attention layer and doing add a normalization. We do this, we just do transpose of this, so that it is appropriate in multiplying. So now we compute here again for this multi-attention, we compute key and query and values. So key is, so we have one more matrix, key matrix, Q matrix and value matrix. We multiply key matrix with XC. So here XC multiply this with XC to obtain the key values. This is how we obtain the query values, and this is obtain the value values. Okay, so see, the keys and values are still from the encoder side, so they still represent how are you, and the values that are to be given are from the query is from the decoder side. This is the query, whereas the keys and values are from the encoder side. Okay, this and this are from the encoder side, and they are based on the question, how are you? Whereas the query is from the decoder side, which says, this is what I am trying to decode, this is what I have decoded so far, you tell me what is to be decoded next. Okay, this is what it does. So we do this and we compute the attention, just as we did in case of encoder layer. There is no masking here. We do simple attention query times key, and normalized scaled with the root number of dimension of k, which is 2, and then you multiplying the value vector. So this is the output that we get of the context vector. So this tells it, this on response to your query, this is what you should generate. Then we do add a normalization and then feed it to feed forward network. This is not the output yet, final output. This is like just the decoder is asking question to the encoder, this is what I have decoded so far, what should I decode the next? And so based on the encoder, what is the input, it tries to give the feedback. Okay, let's move on to the next step. So the next step is we provide the output to a feed forward network. So there are two weight matrices, WD1, and it's passed through a ReLU function, and then the output is passed through another weight matrix, which is fed to this add a normalization layer. So this was the output that we got after the second multi-attention layer and passing through the add a normalization. Assume these two other weight matrices, WD1 and WD2. Then we compute the feed forward layer in the decoder part. So first we pass it through the output, intermediate output, through a weight matrix, pass it through a ReLU function, and then the output from the ReLU function is again multiplied through weight matrix FD2. So we get the final output of the feed forward layer, which is this. Again we have a residual connection, so y prime is again added to this output, and then we do normalization, so we get y double prime, which is the output of this normalization layer. Then what do we do next is we have sort of linear, we have one more linear layer, which is WL layer. Okay, so this is represented by this matrix WL. Okay, and so suppose this WL and it passes through a softmax function. Okay, so WL, it passes through WL, and then WL passes through a softmax function. So this matrix WL, so what does it have? So on the X column we have the vocabulary size. Okay, the final possible outputs, the number of different possible outputs. Okay, so assuming there are only 6 words, how are you and I am fine. So this on we have 6 rows. Okay, so these are 6 neurons in the output layer here, and the input that it takes is I am fine. Okay, then it says at which position which word should be generated. Okay, so we have this y output, which is output of the added normalization layer here. So we transpose it to multiply to the linear layer, which is like this. Okay, so when we multiply, we get this output, and then we pass it through softmax. So when we pass it through softmax, what is softmax? The maximum the words that have maximum probability is the final output. So suppose this is the final output. Suppose let's say at time step 3, that is when fine has to be generated. So we see it gives the output, at the first position it gives the maximum probability to word I, and then second position gives maximum probability to word am, and the third position gives maximum probability to word fine. Now I've just chosen this weight matrix WL such that these words get maximum probability. So that its output looks nice. Otherwise, these are just I've taken other values I've just taken randomly to give you idea of how things work. Okay. So with that, we compute and we complete an end-to-end computation of transformer network. And we'll also do these things in an Excel just to reinforce the idea. That would be a separate activity. So now, what is the advantages of transformer versus the RNNs, that is LSTM and GRU? As I said, important thing is it is parallelizable training. The training part is highly parallelizable due to this multi-head attention. Unlike in RNN, it has to be done sequentially. So all this matrix multiplication can be done in parallel. The multi-heads can be processed in parallel, and all the power of GR or the graphics processing unit GPUs can be leveraged here. Okay. Then, so it also gives performance improvement, and it can capture longer dependencies in a sentence because we are doing all-to-all attention. So we're not doing sequential. So the problem with sequential is as the sentence gets longer, that as the time passes by, it becomes difficult for the network to remember, to pay attention to, or remember dependencies between the earlier parts of the sentence. But here we are using all-to-all attention, so it's able to capture that.